Okay, so in this last video, um, we defined what a linear operator is. Notice that what we're really saying there when we're talking about what a linear operator is, or sorry, a differential operator, is we're just looking at a differential equation and we're asking, what is this differential equation doing to an arbitrary function y? And so the way to find it algebraically, right, is just to move everything with y to one side of the equation and then everything else to the other side of the equation, and what's left on the left hand side is the result of operating on a y, right? This is telling you, it looks like a plus or minus there, that's not a plus or minus, right? So this is telling you what to do with a function y to get an output, right? You take your function, multiply it by a second derivative plus the first derivative, then you subtract cosine of t times the function. Good. Everything with t, notice, is on the other side of the equation, so that doesn't, with t alone I should say, right? This is here because there is a y attached to the cosine. Good. And so what kinds of operators are we interested in? This is the key definition here. So the key definition is the linear operator, and a linear operator possesses two properties. The operator applied to a sum is the sum of the operators, or sum of the result of the operations, and the operator applied to a constant times a function, you can pull the constant out, and we saw that the derivative is a linear operator. Okay, so now we're here to the main point, and the main point of this discussion is definition. A differential equation is said to be linear if its operator is a linear operator. Okay, and so we've just been defining what a linear differential equation is by giving you an example, but now we know a differential equation is linear if the operator associated to it is a linear operator. That's the key definition there. Good. So therefore, we know things like, suppose that I'm going to call my linear operator L for generic linear operator. So we know, for example, the first order linear differential equation looks like y prime plus p of t times y, and we know that's a linear operator, right? Why do we know that's a linear operator? Because that's the operator for a linear differential equation. Of course, we could show that it is a linear operator, right? To show this, right, you would show that L of y1 plus y2 is L of y1 plus L of y2, and L of c times y is c times L of y. Let's show one of them. Which one's harder to show? Maybe the sum is harder to show. We'll show this one. Okay, so L of y1 plus y2, and we're going to show that it's equal to the sum of the operators, right? So that's going to be y1 plus y2 prime plus p of t times y1 plus y2. That's what the operator does to a function. And now we know that the derivative can be broken apart, and we know that I can multiply through by p of t, right? And now I can reorganize. So put the y1s together, put the y2s together, and what do you have? This is L of y1, and this is L of y2. Good. All right. So I'll let you prove the second piece of that. I think we'll do one more example because we haven't shown that something is not a linear operator. How would you show that? So example, show that f of y equals oops, just lost my place for a second. I've just found it. 3y plus y squared is not a linear operator. So how do you show that something is not a linear operator? Well, you have to show that one of the two properties is not satisfied. In fact, neither property will be satisfied in this example, so you can choose either one. Maybe we can take a look at f of c times y, right? Because that means I'm going to take 3 times cy plus c times y squared, and so that's equal to 3 times, let's go ahead and pull out the c because I know I'm going to need that. C times 3y plus cy squared, and that's going to give me a problem, right? Because c times f of y would be c times 3y plus y squared, and you see that these two things are not the same. Not the same. Good. So that's all you would need to say this is not a linear operator. Good. Example. How about f of y equals mx plus b? That's a line, so surely that is a linear operator. Oops. It's not going to be mx plus b, it's going to be my plus b, because it's an operator applied to a function y. Well, is that linear? How about f of c times y? Oops. It's going to get messed up in lots of different ways. How about c times y? That's going to be m times cy plus b. And do you see what's going to mess this up? This is not the same thing as c times my plus b, right? So that b is really screwing things up. And so this kind of confuses students a little bit, because this is the equation of a line, but this is not a linear operator. Not a linear operator. And it's because of the plus b. The plus b is getting in the way, right? Because I can't get the constant, for example, in there. And if I were to take a sum, I would need 2 b's, and I'm only getting 1. Okay, so that's not a linear operator. So just as an side remark, my plus b is called an affine operator. Okay, good. So not lines are not necessarily linear. Okay. I better not say any more about that. Okay, it's because we're talking about an operator. Okay, not a graph. Okay. I suppose I should get to the main point of why we're discussing linear operators. This is the key point. 8 minutes, 25 seconds in. Take note of today, because this is the important thing. The key property of a linear operator is the following. If I take the operator L and I apply it to C1 times Y1 plus C2 times Y2 plus C3 times Y3 plus ... plus CK times YK. By the way, this is called a linear combination. Linear combination of Y1 through YK. That's going to be equal to C1 times the operator applied to L1 plus C2 times the operator applied to Y2 plus CK times the operator applied to YK. And this, my friends, is why linear operators are nice to work with. This, in fact, is called the superposition principle. Jeez, if I can spell. So let's get back to a differential equation. Suppose y1 of t, y2 of t, up to y sub k of t are all solutions to the linear homogeneous DE, that is L of y equals 0. Then another solution will be the linear combination c1y1 plus up to ck.yk. This is going to be another solution. Good. So this is the key. This is a key property. So bringing this back to where we were in the other page, and then we're going to do one more. We have one more quick property and then lots of examples. I wanted to just say last time in the section we said, like, if e to the minus 2t and e to the 3t, I think were the two solutions we looked at, are solutions to our linear differential equation, homogeneous differential equation, then so is c1 e to the minus 2t plus c2 e to the 3t. You see where this is coming from now? This is coming from the fact that we're dealing with a linear differential equation. Sorry about my computer's dinging. Okay, so I'm going to stop there. It's about 12 minutes in. I'm a little bit over, so when we come back, we'll talk about the superposition principle again and take a look at some problems.